Yes, my name's Sky. I'm going to be talking about compositional memory management in lambda calculus and related systems. Probably a better title is a compositional semantics for explicit naming. So one of the most basic things that you can do in a programming language is to bind a value to a name. I mean, this is obviously one of the most basic things you can do, but the thing I want to draw your attention to is the fact that we've got this scope definition here. So in the scope of this body, the name X takes the value 3, but outside of that, obviously, the name doesn't have this meaning as it's out of scope. That means the sort of compiler or interpreter or whatever we're using is sort of managing the names for us. In this talk, I'd like to do something a bit different and introduce a notion of explicit naming in which we have to do all of that ourselves. So with explicit naming, we use explicit operations to manipulate names. So here I'm using bind instead of let just to indicate that I'm doing something explicit. So bind x to 1 plus 2 will create a new name x and assign that value of 1 plus 2 to it. Instead of just saying x plus x, I need to explicitly say read the value from x plus read the value from x. And then when the scope is done, I'm responsible for clearing up that name at the end. So I need to say free x right at the end. And so I've sort of done what the compiler would normally do, and I've done this naming operation manually. The important part of explicit naming is that names are first-class citizens. You can really use a name just like any other value in your programming language. So in particular, if I wrote bind x to 4 in x, this is really an expression that returns the name x, not the value 4. And really importantly, we could then later use the read operator on the return value of that to get back our number 4. That value has not been forgotten, even though that name is out of scope. So what does a language like this do? What can it actually do? What computational power do we have? And is it even possible to reason about this in a nice and compositional way? So here's an analogy to sort of motivate how we might think about explicit naming. So a good analogy is to think of names in explicit naming as sort of like pointers, pointing to some value in memory. So for example, bind x to 7, we can think of that as a memory allocation expression that's going to create a new place in memory and put the number 7 in it, and the name x is now going to be a pointer to that place in memory. Similarly, read x dereferences this pointer, so it gets to the value that's behind that name, and free x deallocates the memory pointed to by x. And so, for example, if I try to read a value after freeing it, that should not be an allowed operation in our language. So a key important point, just to make the distinction between names and pointers clear, is that the value bound to a name absolutely cannot change, unlike with pointers, where we can definitely mutate the value behind a pointer. So under this correspondence, we might think of names sort of like immutable pointers. In this way, we can think of explicit naming as a nice fragment of manual memory management. And so my motivation really for understanding this subject is to better understand how programs modify memory. And so by using this slightly simplified system of explicit naming, maybe we can get a bit more understanding into how programs actually use memory. So I want to go through an example of how a program with explicit naming can run. And so I need to define a semantics. I'm going to be a little bit vague, but the central idea is to use this analogy comparing names and pointers to motivate a stateful semantics based on a heap. So our semantics is going to track through a finite partial function from names to values that determines for each name x what value v it is bound to. So this you can think of just like a heap in a computational interpretation. And the idea is that during every computation step, I'm going to update that heap with the new bindings that I need to add when I've written bind operations. And I might update it by removing bindings if I hit a free instruction. And when I try to read a value from the heap, I just look into the current state of the heap and read the value that's there. And so, for example, I'm just going to underline the part of the expression sort of under reduction at the moment. But the entire expression on the right-hand side, I'm just doing this as a sort of informal computation trace. I think hopefully this gets most of the idea across. And so the first thing I need to do to evaluate this expression is bind x to 7. So I'm just going to put the mapping x maps to 7 in that heap. And so when I later want to read from x, I'll just look at that binding. So that obviously puts the mapping x maps to 7 in the heap. Then when I evaluate read x, that evaluates to 7 because x maps to 7 is in the current heap. And so I then print 7, so 7 gets printed in whatever semantic system we're using, and then I'll finally free x, leaving the end heap after evaluating the expression the same as the initial heap when we started evaluating. So you can see here that this is a very stateful operation, and as type theorists and people who like compositional programs, this is bad. This is a bad state of affairs when everything is very stateful. So just to really hammer the point home, what happens if I do some of this in a different order? So if I did free x before I did print read x, obviously this program would not work because we freed x before we've read from it. So in particular here, when I do free x, I'm going to remove the mapping x maps 7 from the heap. So this means that the behavior of programs with explicit naming is very sensitive to the order of evaluation of sub-expressions. And because the heap is threaded through the semantics sort of linearly, this means that everything is very non-compositional. In order to determine the effect of a composite expression E1 then E2, my initial heap must be threaded through expression E1 in order to get a new heap, which is then used as the initial heap for evaluating E2. This is a very difficult, yes. Yes.
Does it still have scope, or should that be intent?
So I'm being slightly loose with the semantics here. The way that I'm actually doing it is that it's syntactically valid to talk about the word X that denotes the name X in that scope, but the name X will still be valid after the scope ends. I just can't use the letter X to talk about that thing anymore, but I can still use the returned value if it returned X as a name. So you can think of this a bit like pointers. So if I allocate a pointer, I've bound that pointer to a variable name. That variable name representing that pointer will not be valid when the scope ends, but the pointer itself will still be valid. It's the same idea. Okay, so we all sort of agree this is a problem, right? That this is quite non-compositional. So how are we going to fix this? Okay, so one way that I like to think about this problem is to think about how our semantics can be construed as an evaluation function. So we can think of our evaluator as a partial function of this type where it takes an expression and it takes an input heap, and I'm using this one hooked arrow here that's maybe not too clear to see from a distance to denote partial functions, and it's going to output a final heap and a value if this computation succeeds. One way we can write this is as a monadic expression, as a monadic function, sorry, from expressions to values, where the monad is this thing which takes in a heap and outputs a heap. This is the state monad on heaps up to partial functions, which really encapsulates why this is a problem. So can we replace this monad T with something better, something more compositional, while still retaining the properties that we actually want out of explicit naming? And the answer is yes. We can replace it with a monad a bit like this that's decomposed into two parts. There's a reader part on the left, which takes in a context. You can imagine a context sort of like a fixed heap. For technical reasons, I need to put a little bit more information than that in it, but you can imagine it just like a fixed heap. And then on the right-hand side, I have a writer part to the monad. So this not only will return a value when I do an evaluation, but will return what I'm calling an effect, which is a partial function from heaps to heaps that says, if I were to evaluate this expression in this heap, what would the final heap be? But the key thing is I'm deferring execution of that effect. I'm not actually going to do that right now. And in particular, this context here isn't modified when I do sequential sub-expressions. If I do E1 then E2, by a drill, it is exactly 10. It's going on for a while. Do we need to panic yet, or is this okay?
Please continue. You have
Yeah, thanks for your contribution, Fire Alarm. That's been a very helpful question. But yeah, let's get back to it. So the key point is I'm not actually evaluating this effect. I'm not actually doing it now. I'm just sort of saving it for later. In fact, actually, we can get away with doing something a little bit better. We can get away with like an algebraic approximation to these partial functions. I'm not going to go into that here, but that's sort of the detail. Talk to me afterwards, and I'll talk to you about that because I think it's really interesting. You can get partial order on these things. It's lovely. The real cool point is this semantics, even with this algebraic approximation, if you do this, is completely equivalent to the original semantics. There's a minor extra thing we need to do, which is the actual value type. Again, we need to chuck a little bit more data in there. But the key point is we can really replace this stateful monad with this reader-writer pair, and it still works. So let's just give an example of how this sort of works macroscopically. So if we take read x as an expression, the effect of that in a context gamma is a partial function from heaps to heaps. If you give it an input heap that has a binding for x, then it will do nothing to that heap. And if the input heap does not have a binding for x, it will be undefined. Similarly, for free x, if the input heap has a binding for x, the effect in any context gamma of freeing x on that heap will be to remove that binding. And of course, it's undefined otherwise. And this is the crucial part that I was saying earlier, that if we have a sequential composition of expressions, the effect is really the composite of those two actions. And yeah, the same context is used for both E1 and E2. So let's just jump to conclusions. What exactly have we done? So in this talk, I introduced this idea of explicit naming, in which we, instead of the compiler or interpreter, manipulate names manually using explicit operations such as bind, read, and free. In this way, explicit naming can be viewed as a fragment of manual memory management using pointers as names. Under this analogy, the obvious semantics is a stateful semantics with a heap, which is a monadic function from expressions to values. But by replacing this stateful monad T with a better monad, we were able to reduce the dependence on state while preserving the exact properties of that semantics. Paper should be coming soon, but thank you for listening.